Howdy. This video is on isomers. Isomers illustrate how changing bonds or changing the relative orientation of the bonds can change the chemical and physical properties of compounds. After watching this video, you should be able to determine all the isomers for a chemical formula and list what kind of isomers they are. You should also be able to identify the different types of isomerisms. And so isomers are composed of the same exact set of atoms. They have the same molecular formula. Structural isomers, also referred to as constitutional isomers, have the same molecular formula but differ in the bonds that are present. Stereoisomers have the same molecular formula and the number and kind of bonds but differ in the relative orientation of the bonds. And so I think this diagram here illustrates isomerisms really nicely. Again, isomers, same set of atoms. Structural isomers, same set of atoms, different types of bonds. Stereoisomers, same set of atoms, same type of bonds, different relative orientation of those bonds. So please make sure that you understand that flow diagram.
The molecules methyl isonitrile and acetonitrile have the same molecular formula, C2H3N. However, they differ in the bonding arrangements of the atoms. They are examples of isomers, compounds with the same molecular formula that are not identical. Isomers that have different bonds or differ in the locations of bonds within the molecule are called configurational or structural isomers. Methyl isonitrile and acetonitrile are examples of structural isomers. So also are thiocyanic acid and isothiacyanic acid. Structural isomerism is very common in organic chemistry. For example, consider the isomers of butanol with molecular formula C4H10O. Normal butanol, or N-butyl alcohol, consists of a straight chain of 4 carbon atoms with the OH group at the end of the chain. In the isomer that has the common name isobutyl alcohol, the carbon chain is not straight, but has a methyl group bonded to the central carbon of a 3-carbon chain. The alcohol group is still bonded to a carbon at the end of the chain. In secondary butyl alcohol, the OH group is attached to one of the 2 inside carbon atoms in the 4-carbon chain. In tertiary butyl alcohol, the OH group is attached to the central carbon atom, which also contains a methyl group. The 4 butyl alcohols differ in their physical and chemical properties. For example, in their boiling.
And so it's really kind of amazing. You have 4 distinct molecules composed of exactly the same set of atoms, which will have distinct chemical and physical properties.
The molecules.
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the second carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the third carbon position produces 3-methylpentane. Moving the methyl group to the 4th carbon position appears to make 4-methylpentane. But wait, rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the second carbon position produces 2,3-dimethylbutane. Moving the methyl group to the second carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the third carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
And so again, all of them contain exactly the same set of atoms, but will have distinct chemical and physical properties because of the rearrangement of those bonds. Now, when you're asked about how many isomers, remember that atoms tend to have specific types of bonding styles. So you have to remember the structural environments corresponding to formal charges 0. So remember, hydrogen always has just that single bond. Fluorine just has a single bond, 3 lone pairs. Oxygen will have 2 lone pairs, 2 single bonds, or 2 lone pairs, a double bond. Nitrogen will have a single lone pair, and carbon typically has no single lone pairs. So again, when you're talking about structural isomers, I'm just going to constrain to where you have formal charges 0 for all of the atoms. And so when you ask a question like this one, how many structural or constitutional isomers, remember structural, constitutional, same thing, does C5H12 have? The first step you have to figure out is, okay, what kind of bonding is possible? Now, the generic formula CnH2n plus 2 corresponds to when all the carbon atoms are single bonds. And so here you have 5 and 12, so that corresponds to CnH2n plus 2, so we'd expect all the carbon bonds to be single. If you have the generic formula CnH2n, then that means you have one double bond or you have a cyclic group. If you have CnH2n minus 2, then that means you have a triple bond, 2 double bonds, or a cyclic group with a double bond. And so the second part is, after you figure out what kind of molecule it has, you systematically change the structure until you think you have covered all the possibilities. Now, when I'm doing this, I ignore the hydrogen because their number will come out right if I do everything else right. And so for C5H12, again, we figure out all the carbon-carbon bonds should be single. Remember, hydrogen always will just have that single bond. And so we can put the carbon in a row, and we'd end up with 3, 5, 7, 9, 12 hydrogen, which is what we expect. We could imagine, say, this methyl group, this carbon here goes there. Now again, the hydrogen should come out right, 3, 6, 9, 11, 12, and it does. Now moving that methyl group actually gave us a different molecule with different chemical and physical properties. Now we can also move this carbon and say we move it over there. And again, we have 3, 6, 9, 12. We still have 12 hydrogen because all the carbon-carbon bonds are single bonds, and this gives us yet a different compound with different chemical and physical properties. And so for C5H12, we have 3 structural or constitutional isomers. If we're asked about C4H8, that corresponds to CnH2n, and so that means we're going to have a double bond or a cyclic group. And so if the double bond goes between the first and second carbons, that gives us this molecule. If we put a double bond between the second and third carbon, that gives us this molecule. A double bond between the third and the fourth is the same as between the first and second. And then we could actually move, say, start with this one and move this carbon and attach it there. That gives it there. Now notice that even though we changed the arrangement of the double bond, we still have 3, 6, 8 hydrogen, 3, 6, 8 hydrogen, 3, 5, 6, 8 hydrogen. Now, when you do a cyclic group, when you do a double bond, you lose 2 hydrogens compared to no double bond. When you do a cyclic group, you also lose 2 hydrogens compared to not having a cyclic group. And so we have 1, 2, 3, 4 carbons, and 3, 4, 5, 6, 7, 8 hydrogens. And we could also do something like that. Now, it's kind of interesting, for VSEPR theory, we saw if we had carbon surrounded by 4 things, we should expect bond angles about 109.5. Now here, the bond angles are going to be about 60 degrees because we're constraining it to a triangle. And so what that tells you is this isn't going to be really that stable because that bond angle is too small. It's the same with the cyclobutane. That bond angle is 90 when we typically want 109.5 for regions of electron density. And so molecules like this, where you have small cyclic groups, are pretty reactive. We could also ask about C4H9Cl. Now, remember, chlorine often will have just a single bond if it's not in the middle. And so then we can think about, okay, the chlorine is like adding another hydrogen. So that gives us C4H10, which means all single bonds. That would correspond to CnH2n plus 2. But if we put the chlorine here versus here, would give us two distinct molecules. If we move that methyl group over and then put the chlorine on top, that gives a distinct molecule. And if we have, again, this structure here and then put the chlorine here, that also gives us a distinct molecule. And so for that formula, we actually get 4 structural or constitutional isomers. And so again, structural, constitutional isomers, same set of atoms, different types of bonds. And so we consider this bond different from that bond because here we have a carbon at the end, and here we have the second carbon. Now if we put the chlorine here, it's the same as putting it there. Putting the chlorine at this end is the same as putting the chlorine at that end. And so what we mean by different bonds can be a little bit confusing, right? So all 3 of these bonds should be equivalent. And so putting the chlorine here, here, here is all the same. But because this carbon is attached to 2 methyl groups, putting the chlorine here is different than attaching it to that carbon. And so we've talked about the structural or constitutional isomers and the stereoisomers.
Isomers that have the same groups of atoms bonded to one another, but differ in the spatial arrangements of the atoms, are called stereoisomers. In geometrical isomers, the groups are arranged differently with respect to one another. A simple example is cis-strands isomerism, about a double bond in alkenes. Because rotation does not occur readily about the carbon-carbon double bond, cis and trans 2-butene are distinct compounds with differing physical properties such as boiling point. Cis-strands isomerism also exists in coordination chemistry, as in this example of cis and trans tetramine dichlorocobalt 3 ion.
And so this is kind of interesting. Here we have platinum attached to 2 ammonia groups. So the blue is nitrogen and 3 hydrogen, and 2 chlorine groups. Now, if the chlorine's on the same side, then that's referred to as cis. And this compound is actually referred to as cisplatin. Now, in this one, we have the chlorine on opposite sides, and so that would be trans. And so often I think about cis, I think about same as in terms of same side. And so this molecule is square planar molecular shape. And it's really kind of interesting. The cisplatin is actually used as an anti-cancer drug. The transplatin does not have medicinal uses. And so the movie mentioned that you do not easily rotate about a double bond. And so at room temperature, there is no rotation about a double bond. And so when you have the double bond, you actually do have 2 sides of the molecule. And so for the molecule on the left, the chlorine are on the same side, and so we'd refer to that as a cis molecule. The molecule on the right, the chlorine are on opposite sides, and so that would be trans. Now it's also kind of interesting. You'd expect that the chlorine on the left would be more polar because the molecule on the left is more polar because the chlorine is on the same side, and so you might expect the molecule on the left to actually have a higher boiling point. And so how many geometric isomers does, say, 1-butene have? And so we have a double bond between the first 2 carbons. And if we draw it out, we notice that we have 2 hydrogens and 2 hydrogens. And so flipping these does not lead to distinct compounds. And so this molecule has no geometric isomers. Now, if we looked at putting the double bond between the second and third carbons, you notice that here we have the 2 carbons on one side. Here we have 2 carbons on opposite sides. And so it's called the one on the left cis and the one on the right trans. And so we have 2 geometric isomers. And so you can get 2 geometric isomers for each double bond. It's possible you can get a maximum of 2 geometric isomers for each double bond. Sometimes, like in our previous example, you can have a double bond and have no geometric isomers. So to have geometric isomers, the 2 things attached to this carbon have to be different, and the 2 things attached to that carbon have to be different. And then finally, optical isomers. They're stereoisomers, meaning you have the same set of atoms, same types of bond, just different geometric arrangement.
A chiral object is one that is not superimposable on its mirror image. Your left hand is chiral. It cannot be superimposed on your right hand. Many molecules, including important drugs and natural products, are chiral. This is a ball and stick model of a carbon molecule with 4 different groups attached to the central carbon. For example, the 4 groups could be hydrogen, chlorine, methyl, and carboxylic acid. This molecule is chiral. That is, it is not superimposable on its mirror image. The 2 forms of a chiral molecule are called enantiomers. Using special rules, one form is labeled R, the other S. Enantiomers have mostly the same physical properties, but they behave differently in chiral environments. Molecules may contain more than one chiral center. For example, tartaric acid, which is found in many fruits and in wines, has 2 chiral centers.
And so for each chiral center, you can get a maximum of 2 optical isomers. Now, non-superimposable on mirror image seems a little bit confusing. It just means different than its mirror image. And so if we look here, we have a carbon in the middle, and it's attached to 3 different types of things, right? The green things are the same. And so these 2 should be the same.
A tetrahedral carbon atom with 3 different substituents is shown along with its mirror reflection. The mirror is removed and the models are compared. The model is achiral because it is superimposable with its mirror image.
And so again, superimposable means it's the same. Now here we have 4 different things attached to that carbon. And so this will not be superimposable on its mirror image. It will be different than the mirror image.
A tetrahedral carbon atom with 4 different substituents is shown along with its mirror reflection. The mirror is removed and the models are compared. The model is chiral because it is non-superimposable with its mirror image.
And so really kind of interesting, you have the same set of atoms, same type of bonds, just a different arrangement, and there's no way of taking this molecule and making it look exactly like that molecule. And so you got 2 distinct molecules.
A tetrahedral carbon.
And so optical isomers have 4 different groups bound to a chiral atom. Now you got to be careful, it's different groups, not necessarily just the next atom. And so here we have a carbon attached to a carbon which is attached to the 3 hydrogen, carbon which is attached to carbon which is attached to another carbon and 2 hydrogen. And so these 2 groups, we're looking at the entire group, are different. Here we got 3 carbons, and so this one's attached to 4 different types of groups. It's not just the next atom it's attached to, but it's the group that it's attached to. Now they're referred to as optical isomers because if you put one of the isomers in a solution and you pass plain polarized light through it, it would rotate that plain polarized light one way. If you put the other optical isomer in the solution and again passed plain polarized light through it, it actually rotates the light the opposite way. Now it's really kind of interesting. The alpha carbon in all amino acids except for glycine has 4 different groups attached to it. So here you have alanine, and it's got carbon attached to this group, that group, that group, and that group. And so that means that all the amino acids except for glycine are chiral, are optically active. Now what's really kind of interesting is only one of the optical isomers is actually present in proteins from living organisms. And so a question you could see is, which of the following has optical isomers? And so again, what we're looking for is something that's attached to 4 different groups. And so this isn't. Now this carbon is attached to hydrogen, hydroxyl, this group and that group, and so this one should have optical isomers. This does not. This one is attached to, so this carbon is attached to 1, 2, 3, 4 different groups. And here, this carbon is attached to 4 different groups. And that's carbons attached to 4 different groups. And so this one actually has 2 chiral carbons, and so you could actually get 4 optical isomers. And so you could also be asked, does the following display optical activity? And so you're given the structural formula. Structural formulas indicate what's bound to what. If we draw it out, we get this. And we see that this carbon is attached to 1, 2, 3, 4 different groups. And so that should have optical activity. It should have optical isomers. We asked about this one as well. So we draw it out, what it looks like. And we notice that none of the carbons is attached to 4 different groups. And so that will not be optically active. It is not chiral. So please make sure you're able to identify isomers and the different types of isomerisms. Make sure you understand this flow diagram. I think it summarizes isomerisms really well. I hope that was helpful.